So in this example, we are given a truss here that has um, all of its external loads and are applied at the joints, and we're asked to determine what is the force within member EB of the truss. Right? Member EB is the center beam on the center of the truss. Right? So so at first we could look at the section around joint E. So if we took a section cut through BB, so we go through members FE, members BE, and members ED. So we'd end up getting our external force of 1,000 newtons, and then we'd have three internal forces. We'd have one force due to force from along member EB, one due to the force along member EF, and we have one due to the force along member ED. Alright, since all of these forces are concurrent about point E, we know from the method of joints that we really only have two equilibrium equations that we could use. Alright, so we could at most find two unknowns. Alright, we have three unknowns, so we can't do it. Alright, so what we could do is we can take a different section cut. Right? So looking at this truss, alright, so in order to solve this problem, I should say here, before we go on here, we need to determine one of the forces, FEF, FEB, and FED. If we can determine one of those unknowns, we can then solve the problem using these two equilibrium equations. Alright, so in order to solve for one of those unknowns, we're going to take a separate section cut. So we're going to find a section cut A between point A and point along the section cut AA, which goes through members AB, BF, EB, and ED. Alright, and if we do that, what we'll end up getting here is we'll have at point A we'll have our 4,000 Newton force and our 1,000 Newton force. We'll have at point F we have a 3,000 Newton force. Alright, at point we'll have at our section cut we'll have a force that goes from point A to point B. Alright, from point F we'll have another member, and at our section cut we'll draw the force FB, and then at point E our section cut will continue along and we'll have our force FEB. Alright, that would go down to point B here, and then our last part of our section cut AA, we'd have an external or internal force FED. Alright, and then we have to make sure we include our 1,000 Newton force here at point E. Alright, so let me just label all the points of the diagram before we go too far. There we go. Alright, so in this problem we have 1, 2, 3, 4 unknown forces. However, 3 of the unknown forces go through one single point. They all go through point B. So if we sum the moment about point B, we would then be able to solve for our unknown. Right? So if we say, let's see here. So if we sum the moment about point B and set that equal to 0, we can use that to solve the force in member ED. Alright, that's our goal. Alright, so if we look at our problem here, we have a 4,000 Newton load at point A and we have uh, and that is 4 meters away from point B. Since if you use the right hand rule, that 4,000 Newton force would cause a negative moment about point B. We have a 1,000 Newton force that also applies at point A, and that would create a positive moment about point B. So, and that is 4 meters away from point B. We have a 3,000 Newton force that's applied at point F, that if we follow the line of action of that force down, we can say that it is going to create a positive moment of, and since that is 2 meters away from point B, it would have a 2 meter long moment arm. And then we have the only other force we have left is the force ED. All right, so that force ED, let's see. All right, so we'd have so if we took force ED and we brought it all the way down to point C, it goes along the same direction here. All right, that is going to be whatchamacallit, that's going to be 4 meters away. All right, and we know that this angle between these two forces is going to be 150 degrees. We know that the sine of 150 degrees is the same thing as the sine of 120 degrees. The sine of same as the sine of 30 degrees, which is so the sine of 150 degrees is equal to 1/2. All right, so what we end up getting here is FED would cause a negative moment, so we should change the sign here. All right, and it would about point B. All right, and that's our that's how we can solve for FED. All right, so if we move FED to the other side and we divide by 2 meters, all right, what we end up getting is we get minus 16,000 Newton meters plus 4,000 Newton meters, and then plus 6,000 Newton meters. All right, so if you add those up, we get minus 8,000 or minus 6,000 Newton meters divided by 2 meters, which should be equal to minus 3,000 newtons. All right, since we got a negative number, what that means is that FED should be, in fact, in compression, so we could rewrite it as being equal to 3,000 newtons in compression. Right. So what we could then do is we could look back at the equilibrium or the section cut we drew in BB, and we could find the the other force that we're looking for, or the force that we were looking for at the start, which is in the force EB. All right. So to do that, we still have 3 unknowns. So the easiest thing to do would be to solve for we could. So if we look at use that free body diagram here, Alright, we know that both of these forces are at a 60-degree angle relative to the y-axis. So the first thing we could do is since we now know FED, we could solve for FEF first. And once we know FEF, we could solve for FEB. So we're going to sum all the forces in the x direction, alright, and set them equal to 0. So in this case, we'd have FED, alright, times the cosine or the sine of 60 degrees, alright, minus FEF times the cosine the sine of 60 degrees. Alright, so it should be pretty obvious that FEF is going to be equal to FED sine of 60 degrees divided by the sine of 60 degrees. Alright, that's pretty obvious. That will cancel out. Alright, so, and we know that FED was equal to negative 3,000 newtons. So FEF would also be equal to negative 3,000 newtons. And since that's negative, alright, we can say that FEF is equal to 3,000 newtons in compression. Alright, so then our last equilibrium equation we have available, alright, is the sum of the forces in the y direction is equal to 0. Alright, so we have, if we look back at our free body diagram, we have an applied force of 1,000 newtons. Alright, so we have to make sure we include that 1,000 newton force. We also have the two components of the two y components of FEF and FED. So FEF is going to be equal to negative FEF times the cosine of 60 degrees, which I believe is a half. Alright, and then minus ED times the cosine of 60 degrees minus FEB. Alright, we're going to rearrange this equation to solve for FEB. Alright, so we'd end up getting FEB would be equal to minus 1,000 newtons minus FEF and FED are both equal, and they're both equal to negative 3,000 newtons. Alright, and cosine 60 degrees is just 1/2, so we get minus negative 3,000 newtons again times 1/2. Alright, both of these would turn into positive numbers, and we get minus 1,000 newtons plus 3,000 newtons here. Alright, so we end up getting a positive 2,000 newtons. Alright, and that was what we were originally asked to solve for. So using the method of sections, it saved us the tediousness of having to go and solve for a bunch of different joints. We had to solve for at least 2 or 3 joints before we could solve for the force within EB. So that saved us a lot of time by using the method of sections.